Alright, good day guys. When we talk about vector graphing, it's just like a normal way. Literally we said the addition of vector, you add them together, normal matrix addition. But how do we tend to visualize it? To give a detailed information of what we are trying to explain to you, because literally a vector is a value and also with respect to direction, do not forget. So how do we represent a 2D vector that is based on a normal x and y plane? Now there are certain things you need to understand is that how do we know a vector with a normal value? What differentiates them is the arrow. At times, most cases, when people do write it in bold letter. So when you want to represent a vector, we use arrow literally more often. So whenever you see a particular arrow in a particular certain alphabet, you should know that what it's talking about vector. Now also again, if you want to represent vector in full details, you need to describe two certain things. It needs two numbers, that's for 2 dimension. And like I told you that the space in plane deals with a zero vector at start. So the arrow from the zero and the zero what point, that's the origin. You can say the origin, the point in space. So let's assume we have a particular vector v equals to 4 and 2, two numbers, and vector w equals to -1 and 2. Now if you want to add the particular vectors together, there are certain things you need to understand also again. Right from a little bit recap, we call something head to tail. Just like me saying where one person's problem ends, that is where the other person's what own begin. Now head to tail, that is where vector v ends, you have to place w to continue from that point. Are you get what I'm saying? And literally also where vector w even ends, you can actually place vector v in order to move with respect to that point also. Now let's look at this graphing under v plus w. Now literally when you look at this now, you should know that our vector v has what 4 and 2, and x what x axis of 4, and what you have y axis which is 2, x axis which is -1, the negative x axis, and what we still have what a y axis of what of 2. Now literally now when you are looking at this certain particular thing, you see that the vector v is represented with what 4 and 2. So if you are to look at this now, when we trace it, you have this particular arrow moving through this particular point as a vector v 4 with respect to 2, that particular point, as you can see. So if you are to look at now, when we look at w is what 3 is -1 and 2, that's -1 with respect to 2, that is that of what the w. Then we have this particular point for what for w, as you can see. Now we need to find the addition. This is the normal representation of the vector. How do we add them? What is the addition? Actually at times we usually call the addition a resultant. Are you with me? Now like we said that where one's problem end, that is where another one continue. Now this is where the first vector v ends. Now we can place vector w with respect to it. And if you see, when we place vector w with respect to where vector v ends, you have a vector w here. And also this is where vector w ends. If you place vector v a particular point here, you should see that what this particular side and this particular side, they are equal. This particular side and this particular side, they are literally not that equal, but just trying to put a normal representation of a particular vector. Starting from here, this is the head to tail, then what head to tail. So we have a vector w, we also have a vector v here. Now the diagonal of this particular shape that is being made is what will give us the addition of the vector, or we can say resultant. So when you draw a particular certain point from the origin straight down to where they hit themselves, where they meet, this is what the addition of the vector v plus w. So in the normal way, when you want to add it, you have normal 3 and 4. When you want to add it normally, but when you want to visualize it in graph, this is the normal visualization of a particular value. And literally you see that what this diagonal is the vector additions, and literally we call this what a shape of parallelogram. This is normal addition. Then let's check out subtractions also. So literally, if it is a subtraction, then it's actually easy. The normal way we have our normal vector graphing, and if you know, you have to know something that when you reverse a particular vector direction, you get the inverse of the particular vector. So when we are considering the inverse of w, as you can see, with respect to the direction, you have negative what of vector w. And from that aspect of points, when we are considering, like I told you, we are considering vector v and also the inverse of vector w. Now we know that what this is where the vector v stops. Then what you should know that surely the continuation going down to this particular point with respect to the negative direction of vector w will give us a negative vector w, and also again the point from here to this particular point will give us a vector v. So the combination, or we're just saying the linear combination of vector v and w, you have, it's just like you saying v plus negative w, which will still give us what v minus what vector v minus what vector w. And just like normal subtraction, you have what 5 and 4 minus 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 1, you have 5, then 2 minus 2, you have what? 0. So that is the literal aspect of what graphing the vector in two-dimensional plane. And there are some things we need to just understand a little bit, which is we need to understand that the zero vector is too short for us to draw. That's why it does not have any magnitude or any direction that we need to assign to it. And also again, a particular vector plus a zero component, a zero numerical value will still be equal to that vector itself. And also again, let's assume let's assume it's a particular vector v. When I multiply this particular vector by 3, it means that what the length of the vector what will triple. Again, I'm saying if it's 2 times the certain vector, it will double. So when you, like I said, when you reverse the direction of a particular vector w, you will get the inverse of the particular vector. So that is some one or two things that you need to know under graphing of a particular vector. Alright, so when we talk about vector in a three-dimensional space, it's just like we say we are not dealing with x and y plane anymore, but x, y, z, and literally you should know the components will be x, y, and z, v1, v2, and v3. So if you have a particular vector v and vector w, this is like what we call a normal 3D dimension. So when you add them, normally see the normal addition of the vector, or just in a 3 components. And literally the origin will be with respect to also 3 components 0, 0, 0. And the combination of that vector, now it has to be a 3 categorical combination, because 2D 2 categorical combination. So considering typical linear combination of 3D vector, we need 3 particular vector. So you can say let vector u be this, vector v be this, vector w be this. So vector u plus 4 vector v minus 2 times vector w. This is a normal linear combination of what? Of a 3D vector. And don't forget that this vector u here is just like you saying 1 times also vector u. How you get what I'm saying? And it's just like we say, we can say cu plus let's say ev and plus just say kw. So this is just like a normal linear combination of 3D vector. So literally the graphing might not be that clear, but let's assume we have a particular vector v and vector w. Unlike the way we do the normal 2 dimension, when it comes to 2 dimension, you are considering 3 particular components, and literally the graphing of v will be different from when it is in when it is in a particular 2 plane, literally. So this is just like a normal preamble of what we just need to understand literally.